15 because section over here, upward 15 treated as positive, section the UDL portion is there acting downward, so minus sine 10 into x, and this shear force is 0, is equated with 0. We got 15 is equal to 10x and we got x is equal to 1.5. So now you just see, visualize the concept by using both the methods, either used by taking a section at xx, because if we are taking a section xx, our figure looks like this, and we are generating the equation shear force xx at xx section, and we are able to find out the value of x. Or if you know that relationship of shear force which has been given by straight line, we are using the concept of maths and we can able to find out the value of x is equal to 1.5 meter. So from this we can conclude that at 1.5 meter from A we can achieve maximum bending moment. Our next step is to plot bending moment diagram. So let us go over here and let us plot the bending moment diagram over here. The given beam we know the reactions also. And these are the basic lines, important lines, where we have to write down the values and join those values we have to plot the diagram. Baseline, positive values all above the baseline, negative values below the baseline. Now next point, let us take a section. As we know, support is there over here, the value is 0, but even though, let us take a section xx, distance x from A, and our figure first one is like this. Now shear force at xx is equal to our intention is to not to find out the shear force, intention is to find out bending moment. Xx is equal to 15 into x is the first moment produced because of 15 treated as positive. Why positive? Section left creates clockwise moment, sagging nature, minus 10x square by 2. How this 10x square by 2 will be there? Because 10 into x is nothing but the load multiplied by the perpendicular distance x by 2. So 10 into x by 2, that is 10x square by 2, that creates the section left anti-clockwise moment, hence negative. So we achieve 15x minus 5x square. Now this is the equation, just equation of x square, means equation of parabola. Now you just put x is equal to 0, we find out BM at A is equal to 0 because x is equal to 0, and we achieve the same answer. Now in the previous case we found over here that x is equal to 1.5 meter, the shear force is 0, so I have to find out the value of bending moment at 1.5 meter to find out the maximum value of bending moment. So In this case, if I will put the value of x is equal to 1.5, the bending moment is equal to 15 into 1.5 minus 5 into 1.5 square. And by solving this, we found out it is 11.25 plus sine kilonewton into meter. So we achieve at distance of 1.5, the answer is of 11.25. Now next, I have to put because this equation, this equation is valid up to B point, because up to A to B single load is given to us, that is of UDL. So this equation is valid up to the B point. So I have to put x is equal to 4 meter in this equation. So BM at B is equal to 15 into 4, 5 into 4 square. Now this is equal to 60 minus 80, and we achieve is minus 20 kilonewton into meter. So right now we achieve this ordinate is of 20 minus sign below baseline, and I have to join these 3 points 1, 2, 3 using parabola, because the x square term will be there over here. So if I will join, I join like this. This is the variation of bending moment between A and B, and we are finding out this variation. We can find out only single equation, as single load is there between A and B. Next, what is the value at C? Obviously we know the value at C is 0. The value at C is 0. But if you want to check it out, then we have to take the moment at C, and we found out the value by taking the moment at C. Now, what is the variation between B and C? For that, we have to take a section over here, XX. Now visualize, if I will take a left section, forget the right section, only left, then we have a load, point load, UDL, another point load, and this portion of UDL creates an equation with the x. So we can solve the equation, but slightly lengthy equation, we can get it out. But if we take a section from the right side, only single load is there, UDL. So let us take a section from the right side, taking an x from C, and see what happens. So now my figures look like this. This is my section, this is load 10 kilonewton per meter, this length is of x meter, bending moment at xx is equal to 10 into x into x by 2. Now it is very much important, because sign convention, the section creates a clockwise moment, but section right clockwise, the clockwise is from the right side, that creates the hogging moment. Negative sign is equal to minus 5x square. Now if I will put x is equal to 0, my bending moment at C, because x is equal to 0 means it is at over here at C, it is 0. And if I will put x is equal to 1 means I am interested to find out the ordinate at the center. What is the ordinate at 1 meter from C? Then we get it, bending moment is equal to minus 5 into 1 square, that is the minus 5 kilonewton into meter. And if we take x is equal to 2, we can achieve bending moment at C is equal to minus 5 into 2 square, that is equal to minus 20. The same answer that we achieve by taking left section. So now at 1 meter we achieve the value or the ordinate is of 5. Now this is the section. This 1 point, 2 point and 3 point I have to join. How to join? Because it is a 5x square is the equation, this one, joined by parabola like this. So now this is our bending moment diagram and this maximum is of 11.25. So this is our bending moment diagram that we achieve by using the basic concept. In this bending moment diagram, one point it is remaining, that is to found out, because this point, recall, please recall, we discussed about this point. What is the name of this point? This point is known as point of contraflexure or point of inflation, the point at which bending moment diagram changes its sign. The point at which the bending moment diagram is 0 by changing its sign is known as point of contraflexure. And my intention is to find out this distance x. How to find out? Now in the previous cases, the relationship which has been given by inclined straight line, but here the relationship is of parabola. So we cannot use a pure mathematics, or by using the triangles we cannot find out, because this is parabola. So we have to take a section. Now first important point that we have to observe over here, that my point of contraflexure occurs between A and B. It is much important, our observation. So we have to take a section between A and B. We have to find out the equation of bending moment, and then it is equated with 0, and then we have to find out the value of x. So now our first observation is that the bending moment is 0 between A and B. So this figure, free body diagram, we can use to find out point of contraflexure. How? That is we understood over here. We have a figure, so we have an equation of bending moment is equal to 15x minus 10x square by 2. This is the basic equation of bending moment, variation of bending moment between A and B, which is equal to 0 at certain point, and I have to find out the value of x. Therefore 15x is equal to 5x square. By simplifying, we get x is equal to 3 meter. So we get x is equal to 3 meter very easily, that at 3 meter from A my bending moment is 0. So now I think you will understood very well how to find the bending moment diagram. Please see in this particular PPT. This is the shear force diagram. X is equal to 1.5 meter. Extremely sorry. Where shear force is 0. There is a reaction over here. Sudden change in the shear force we can observe over here. Over here, reaction is there. Sudden change in the shear force diagram. So if we revise the basic fundamentals, basic concept, the first, the point load or the point or the section at which the point load is acting, the shear force diagram suddenly changes. Second, UDL, The shear force diagram variation is given by inclined straight line. Next, bending moment diagram. Visualize this bending moment diagram. It is at most important to visualize over here. Please recall the concept of shear force and bending moment for simply supported beam. In case of simply supported beam, the bending moment values are 0 at their respective supports, which is not possible over here because there will be over here some overhanging projection. Because of that, there will be a certain moment is there, means the bending moment is not 0 at this particular support where there will be a overhanging is there. When there is a simple support is there, on one side there is no support is there, yes, definitely the bending moment is 0. Next observation. For a UDL, the variation of BMD is given by parabolic nature. And the third observation, the point at which bending moment is 0, that point is known as point of contraflexure, and we found out x is equal to 3 meter. So now I wish you will able to draw the shear force and bending moment with point load and with uniformly distributed load. So let us go ahead with the next problem. So our next problem over here, visualize a problem very carefully. After this support there will be a certain projection is there, no support over here, means this beam is known as overhanging beam. The first observation. Second, this overhanging beam subjected to two different loads. First is this point load, another is uniformly distributed load, and our intention is to find out the shear force and bending moment at a given section or at all sections, and then we have to plot shear force and bending moment diagram. So step number 1 for this kind of problems is we have to find out the support reaction by using the conditions of equilibrium.